We introduced Speedy Deformable 3D Gaussian Splatting, a technique that accelerates the rendering speed of deformable Gaussian splatting from 20 to 276 frames per second via temporal pruning and motion grouping, all while preserving the superior image quality of per-Gaussian neural motion. Our CVPR 2026 paper, open source code, and interactive video results are available at SpeeDe3DGS.github.io. To reconstruct dynamic scenes from monocular video, dynamic Gaussian splatting extends a set of 3D Gaussians with a deformation network that predicts time-varying offsets for the means, rotations, and scales at each time step. Among motion models for the deformation network, neural motion is slow but produces high visual fidelity, while non-neural motion is fast but produces lower visual fidelity. Speedy Deformable 3D Gaussian Splatting, or SpeeDe3DGS, bridges this efficiency fidelity gap through three complementary modules that jointly reduce redundant inference, stabilize temporal consistency, and distill neural motion into compact rigid representations. Our first module, Temporal Sensitivity Pruning, removes redundant Gaussians by aggregating the gradient sensitivity across both space and time. For each Gaussian, we compute its temporal sensitivity pruning, or TSP score, as the second-order sensitivity of the L2 reconstruction loss to its projected value across a set of training poses and time steps. These gradients capture the total contribution of each Gaussian to the dynamic scene reconstruction. We periodically prune low-contributing Gaussians during training, reducing neural inference and boosting rendering speed. Our second module, Temporal Sensitivity Sampling, enhances pruning stability by perturbing timestamps during sensitivity estimation, suppressing floaters and improving temporal coherence. Floaters are unstable Gaussians that appear stable under observed motion but drift at unseen timesteps. Since our temporal sensitivity pruning score is calculated on a set of training poses and timesteps, it does not reliably capture floaters. Temporal Sensitivity Sampling, or TSS, introduces temporal perturbation during sensitivity estimation by jittering the timestamp input to the deformation network. This temporally jittered sampling reveals unstable primitives early in training, encouraging robust pruning and suppressing floaters. The noise magnitude anneals as training progresses, ensuring precise reconstruction in later stages. Pruning with TSP and TSS improves PSNR and SSIM on the NeRF-DS dataset while rendering 6.35 times faster and using 11.95 times fewer Gaussians. Rendering speed on the Bell scene accelerates by 8.4 times from 33 to 277 frames per second. SSIM and visual fidelity improve despite using 11.6 times fewer Gaussians. Training time is also halved. Pruning with TSP and TSS also removes floaters that are present in the baseline deformable Gaussian splatting scene. Our third component, GroupFlow, clusters Gaussians with similar motion trajectories, distilling per-Gaussian neural deformations into shared groupwise SE3 transformations. GroupFlow consists of 4 steps. We start with a dense dynamic Gaussian splatting model with learned per-Gaussian neural motion. Each Gaussian is represented in 4D as a sequence of mean positions. Then, we initialize J control trajectories and assign each Gaussian to the most similar control point using our trajectory similarity score. Next, we fit a groupwise SE3 flow with shared rotation and translation to each group using Umayama alignment. Finally, we jointly optimize the shared flows with the dynamic scene. This reduces the number of transformations per frame from N per-Gaussian neural deformations to J per-group SE3 transformations. GroupFlow accelerates rendering speed on the NeRF-DS dataset by 8.58 times while maintaining the temporally coherent, high-quality motion reconstruction of per-Gaussian neural deformation. Our full Speedy3DGS framework, which combines temporal pruning and GroupFlow, achieves 10.68 times faster rendering speed and 59% faster training than deformable Gaussian splatting. Furthermore, it maintains perceptual quality despite using over 11 times fewer Gaussians and replacing expensive per-Gaussian neural deformations with efficient groupwise SE3 transformations. In the Bell scene on the bottom left, notice that adding GroupFlow retains the floater removal capability of TSS while accelerating rendering speed to 15 times faster than the original deformable Gaussian splatting model. On the HyperNeRF dataset, Speedy3DGS achieves 29.21 times faster rendering speed and 73% faster training. On the chicken scene, Speedy3DGS preserves the visual fidelity of deformable Gaussian splatting while rendering 33 times faster, reducing training time by 76%, and using 11.6 times fewer Gaussians. Across the 50 scenes and 5 datasets in the monocular dynamic Gaussian splatting benchmark, Speedy3DGS achieves over 100 frames per second faster rendering speed and higher image quality metrics than all non-neural motion baselines. Speedy3DGS is based on our group CVPR 2025 papers, Pop3DGS and SpeedySplat. If you're interested in learning more about efficient 3D representations, we encourage you to visit these projects. Visit our project page at SpeeDe3DGS.github.io for our full CVPR 2026 paper, open source code, and interactive video results.